Hello everyone. This will be the last lecture during this Unit 6 and then we will get ready to take a quiz. I know I said the other day that that was the last topic, but I had a few other items to discuss with you guys that will be on the quiz, so you're going to have to understand these. They will probably not be, I don't even know if they're on any of the worksheets or on the review, but these are terms that you're going to have to understand as we take the quiz over this stuff. So make sure you take your notes over it and have this stuff down so that you can successfully negotiate these questions. All right, so we've been talking about spherical lenses and mirrors pretty much the entire unit. That's been a majority of the topics that we've been covering. But I wanted to go through a couple of things that are issues with that. So first thing we need to talk about is the two types of aberrations that occur due to spherical lenses and mirrors. First of all, we have talked about how they are spherical, and we've used the radius of curvature of the lenses and the mirrors in order to calculate focal points. Unfortunately, as we get closer and closer to the fringes, as this curves around, we end up with not this nice clear focal point, but we end up with multiple focal points depending on where we're located at. Okay, so where this diverges the most is here on the fringes of the actual lens. So you will see in this picture, this is more representative of what the actual focal points give you due to a lens. So the thinner the lens, the less aberrations we have because we're shining the light more towards where it's not getting into the curved part of the fringe up here, okay? But a thicker lens is going to have a greater spherical aberration because you're getting into these parts where it's starting to curve over a lot more, and it's going to generate a bunch of different focal points. Even with a thick lens, one way that we can adjust this is to have a diaphragm that we close down where we block out the rays from the fringe and we just focus in on the rays here in this part of it. Obviously, with a telescope, we need a pretty thick lens if we're going to use a telescope that's based off a lens instead of a mirror. But by using a diaphragm, we end up cutting out a lot of the light that we get from space in order to adjust and see the image. So it's kind of a catch-22. You use a thicker lens to get a larger image that forms, and so that you can see further out. But then you have to use a diaphragm to end up eliminating some of the spherical aberration that shows up, so that you can actually focus in on the image that you're wanting to see. This does also occur in mirrors. Once again, the greater the curvature of the mirror, as we get into these fringes, you will see that there's many focal points. One thing that we can do to adjust this, though, instead of a diaphragm, is just not to use a spherical lens or mirror. Okay, so instead, we can use a parabolic shaped mirror, and then we can also get these light rays to focus in on one single focal point. Okay, so really, we've been dealing with these spherical mirrors and lenses. We really want to design it as a parabola. Okay, so, and we're not going to go into all the math on all of this stuff, and we will still use our spherical lenses and mirrors. But this is the proper design for a mirror in order to generate light at a specific focal point due to the spherical aberration. We have another type of aberration that obviously won't occur in mirrors, but does with lenses. And if you are in photography, this is an issue that, sometimes we take pictures and we end up with a red and a violet fringe, depending on where we're looking at, which part of the image we're focused on, due to chromatic aberrations. Now, what we should understand by now is that the refractive index is different for all colors since light disperses as it refracts through a lens. Okay, once again, this is not going to happen on mirrors, but it will happen with a lens due to the refractive index, remember, is going to be different for all colors of the spectrum. Remember, your higher energy waves will refract. I used the wrong term there. Your higher energy waves will refract more and will bend towards or away from the normal, depending on which way we're going from a specific index of refractions. So what we end up with is different focal points for the red and different focal point for the violet and all the other regions of the spectrum. There are ways to eliminate this in like Photoshops and different programs, and you can also do different things with the lens to try to eliminate these chromatic aberrations, okay? But this is something that photographers have to take into account. All right, last topic. Color mixing, and you will need to know these. When we're talking about primary colors of light, red, green, and blue are the primary colors, okay? Now, we're not talking about pigments here. So if you're in art class, your pigment color, primary colors, are going to be different, okay? But when we're talking about light, red, green, and blue are the primary light colors. When we combine all three of those primary light colors, we will end up with white light, okay? So red, green, and blue, all overlapping, will form white. Now, we can also form secondary colors from this, just like we can with pigments. Red and blue will combine to form magenta, not violet, it's magenta. Red and green will combine to form yellow, and blue and green will combine to form cyan. All right, so if I have a light source and I just have a red filter, okay, so I will allow only red to propagate through that filter. But if I take the red filter and a blue filter and I overlap them, I will get magenta that ends up shining through. Okay, now this is color adding. When we are talking about color subtraction, this is what we normally see. Materials will absorb specific wavelengths of light, and then that color will be subtracted, and we will perceive the color of the material based off of what light is reflected off of it. So this is why I always joke around about how my wall in my room is blue. Okay, when you sit there and you look at it and you go, no, that's the most annoying yellow color I've ever seen. All right, and the reason I say it's blue is because the primary colors that are reflected off of the wall are red and green, and those combine to form yellow, but the wall actually absorbs blue wavelength of light. So what we perceive as yellow, we can also say it's blue because that's the color that it actually absorbs. Okay, so this is the way it works. We have red, green, and blue light coming in, okay? If we absorb the blue light here, the two reflected colors are red and green, and we should know from the addition that red and green are going to form yellow. Okay, so this is something you're going to have to kind of work around with and think about. I'm going to show this to you real quick, so I'm going to make me disappear here for a second. All right, so I went to our nice ophysics.com website here for the simulations. So got primary colors, red, green, and blue. Okay, so remember, if we overlap red and blue, we get magenta, okay? If we overlap the blue and the green, we get cyan. Okay, now overlapping the green with the red, we form yellow. And if we overlap all three of these, we get our white color in the middle, okay? So anyway, all three of the primary colors add up to equal white, and you have yellow, cyan, magenta as the secondary color, and red, green, and blue for your primary colors. Okay, so once again, make sure you know all of those. They will be tested, so make sure you have those things down. All right, that is it for Unit 6 for me. I will be posting a review sheet, and we'll have our quiz later on in the week. All right, talk to you guys later.